Dark energy may not be constant. If it changes, the universe could fade into darkness, reverse into a collapse, or, under an extreme model, tear itself apart. Let's separate what we know from what we're imagining. Dark energy may not be constant. If it changes, the universe could fade into darkness, reverse into a collapse, or, under an extreme model, tear itself apart. Let's separate what we know from what we're imagining. By the end, you'll know what each ending requires, why none is confirmed, and which measurements could distinguish them. The real question isn't simply whether expansion continues. It's how acceleration changes. Here's the established part. The universe has expanded since its hot early phase, and observations show that expansion is now accelerating. Something makes distant galaxies separate faster than matter's gravity alone predicts. We call that unknown cause dark energy. The name doesn't identify a substance. It's a label for whatever produces the observed acceleration, whether that's vacuum energy, a changing field, or altered gravity. The standard cosmological model uses the simplest option, a cosmological constant. Empty space carries a fixed energy density. As space grows, matter thins out, but that vacuum density stays unchanged. Cosmologists summarize dark energy with a quantity called W, comparing pressure with energy density. For a cosmological constant, W equals -1. A different value, or changing value, points elsewhere. No telescope photographs dark energy directly. Astronomers reconstruct its behavior using supernova distances. The ancient microwave background, galaxy clustering, and a feature in cosmic structure that works like a standard ruler. Recent DESI analyses strengthened hints that dark energy may evolve when its galaxy map is combined with microwave background and supernova data. But a hint isn't a discovery, and combinations give different strengths. Small calibration shifts, supernova samples, model choices, or hidden systematic errors can move the answer. So the responsible statement is narrow: changing dark energy is scientifically plausible, interesting, and currently unconfirmed. Now for the thought experiment. Imagine dark energy has a control knob. We'll hold everything else as steady as physics allows, then turn that knob 3 ways: constant, weaker, and stronger. First, leave the knob alone. With a positive cosmological constant, expansion keeps accelerating. Distant unbound galaxies eventually cross our observable horizon, not by vanishing, but because their future light never reaches us. Gravity still protects bound neighborhoods. The Milky Way's local group doesn't get stretched apart by ordinary constant dark energy. Yet the wider universe gradually disappears, leaving one merged galactic island in view. Inside that island, stars exhaust their fuel. New stars become rare as usable gas runs out or gets locked away. This isn't a sudden apocalypse. It's an extraordinarily long dimming. Far later, stellar remnants and black holes dominate. If Hawking radiation works as expected, even black holes eventually evaporate. The cosmos approaches a thin, cold state with little usable free energy. People call this the big freeze or heat death. The broad direction follows from constant dark energy. But the fine print depends on uncertain physics, particle stability, quantum gravity, and black hole behavior. Now turn the imaginary knob down. Suppose dark energy weakens as the universe ages. Acceleration could slow. That change alone wouldn't guarantee a collapse. Expansion has momentum, and matter keeps becoming more dilute. If dark energy stays positive but fades, the universe might still expand forever, just less aggressively. Galaxies would separate, stars would die, and the ending could resemble a slower version of the Big Freeze. A big crunch needs more. The effective cosmic push must weaken enough, or change character, so gravity can halt expansion. That possibility depends on the field's future behavior, which present observations cannot map indefinitely. Picture the turnaround. Galaxy separations stop increasing on the largest scales. Then the cosmic web contracts. Background radiation grows hotter, encounters become more frequent, and the night sky becomes progressively brighter. Eventually, galaxies collide throughout the compressed universe. Temperatures and densities soar. But calling the final state a simple reverse Big Bang goes too far. Unknown high-energy physics controls the last stages. So the crunch is allowed by some changing energy models, not predicted by current evidence. And even if contraction began, speculative effects might produce a bounce, a singularity, or something our equations can't describe. Now turn the knob upward. In a hypothetical phantom energy model, dark energy's density increases as space expands. Expansion then feeds the very component driving expansion, producing a runaway effect called the Big Rip. The tearing would follow a scale order. First, galaxy clusters lose their grip. Later, individual galaxies become unbound. Only much nearer the proposed end would star systems and smaller structures face disruption. In the most extreme mathematical continuation, planets separate from stars, material bodies come apart. And even atoms may fail to remain bound. Space doesn't explode outward from one center, expansion intensifies everywhere. That sounds dramatic because it is. It's also deeply conditional. A big rip requires a persistent equation of state on the phantom side of -1, extrapolated far beyond any observed cosmic era. Some phantom models also bring theoretical problems, including instabilities, unless a deeper framework fixes them. So this ending belongs on the possibility board, but it shouldn't be presented as the universe's scheduled fate. There are stranger options. A dark energy field might settle into a new value, oscillate, or undergo a transition. Each behavior changes expansion differently, and none can be selected merely because its ending looks interesting. Vacuum decay is another theoretical possibility, separate from ordinary evolving dark energy. A lower energy state could spread through space, changing physics locally. We have no evidence that such an event is approaching. And perhaps dark energy isn't energy at all. Gravity may behave differently across enormous distances. That alternative must explain both cosmic expansion and the observed growth of structure without breaking successful local tests. This is where new maps matter. ESA's Euclid measures galaxy shapes and clustering across cosmic history, testing both expansion and structure growth. The goal is to see whether the -1 setting truly stays fixed. DESI's larger galaxy samples, supernova surveys, and future Roman observations can attack the same question differently. Agreement across independent methods would be persuasive. Disagreement could expose calibration trouble or genuinely new physics. The decisive clue isn't one spectacular image. It's a consistent pattern in distances and structure across time, surviving new samples and systematic checks. Cosmology often advances through stubborn agreement between quiet measurements. For now, the simplest constant dark energy model still provides the baseline. Evolving models deserve serious testing because the hints are intriguing, not because the big crunch or big rip has suddenly become a forecast. So, can dark energy change? Possibly. We don't yet know. Its measured behavior over the next stretch of cosmic history will decide whether our best forecast stays a long freeze or needs a rewrite.